Alright, so test 4, again, the blank test is posted. There's a PDF of it on the Calculus 1 page. You can look at it and try it for yourself before you look at this. And there's a PDF of this point posted as well. If you don't want to listen to me talk about it, then don't. Certainly you might get more out of just reading it. Listen to me jibber jabber about this. So test 4 in Calc 1 with me is on integral calculus. So it's, of course, by far the thing you must know. I would say it's probably the most important part of Calculus 1 to have totally fresh in your mind. Although, honestly, every technique of differentiation is important for Calculus 2. So those two computationally, you really, really need to have down integration and differentiation. The definition parts of integration and differentiation also matter, but they're less damaging to you if you don't know those. I'm not saying not to know them, I'm just saying that if you don't know the calculational part, it will steal your points much faster. So, first priority for me as I think about students reviewing Calc 1 is to make sure that the product rule, chain rule, quotient rule, U substitution, basic anti-differentiation, application of the second fundamental theorem of calculus, these things, the min-max theorems, like those are the major things that you have to have down. All right, anyway. So here's a initial value problem. I give you the derivative is that, I give you the value is 0. So basically the idea is, and I differentiate this, f of x is 1/2 x squared plus e to the x plus some constant, but then f of 0, 0, which tells me plugging in 0 that the constant has to be -1. So there it is. Here is a FTC part 3 question in my terminology. If I'm differentiating an integral of variable bounds, all I do is I plug the upper bound into where t is, right, like that, and I multiply by the derivative of the upper bound, which is cosine, and then I subtract this expression with x squared plugged into it. X squared is x to the 4th, squared of x squared, and then I multiply by 2x. This is, again, what I refer to as FTC part 3, or you could think of it as FTC2 and the chain rule, whatever floats your boat. Here's a question about properties of the definite integral. I like this one a lot. This one's nice because it really tests whether you understand the properties without letting you rely on some silly formula. So you're given that the integral of f is 3 from 0 to 1. You're also given that 1 is less than g is less than 2 from 0 to 1. Given this information, you're supposed to find the maximum minimum values possible for g plus f. So the integral of g plus f is going to be the integral of g plus the integral of f, right? Now you know the integral of f is 3, so this is g plus 3. But, so you get I minus 3 is equal to, I being the integral of g that you're trying to put what are we trying to do here? Oh no, I is this integral. Sorry, I'm an idiot. So the thing I'm trying to put bounds on, minus 3 is equal to that. But of course, the integral of g I can bound by the sort of the squeeze theorem of sorts for I don't know what you want to call it, the inequality preservation property of definite integrals. So this is 1 times. It's hard to see here, but it should be 1 times b minus a and 2 times b minus a. If the integral we were working with was 0 to 2, or let's say 0 to 3, then this would have been 3 less than or equal to integral from 0 to 3 g of x dx less than or equal to 2 times 3, which would have been 6. Just to warn you, this is multiplied by 1 and 1 here because it's like property, oh man, I want to say property 2 or 3. I was talking about properties of definite integrals. So this problem's not optimal because some students would have gotten this right for the wrong reason. Oh well, I can't time travel, so I can't fix it. So add 3 for less than or equal to that integral I'm trying to figure out, less than or equal to 5. So lo and behold, between 4 and 5. All right, problem 4. Use the definition of the definite integral in FTC part 2 to calculate the following infinite sum. So this is kind of a backwards problem. So basically the point is that this right here we're understanding this to be the Riemann sum for some definite integral. So you gotta use your imagination and go, aha, this is f of x sub I, and this is delta x, right? So there's many different interpretations possible, but they'll all come with the same number. I mean, it's a convergent sum, I mean, this is a particular number. It doesn't matter how you represent it. You're still gonna find 117 over 3, but this is by no means unique. This is a kind of a challenging problem. Um, I don't think this needs to go on quiz 1, but I do think we run up against this later. We run up against things like this later. Um, no, I really I might put one of these on quiz 1. I actually might. It might be good to have you guys be aware of this earlier rather than later. So anyway, the point is just to kind of think backwards of this as a Riemann sum. Identify f of this is like x sub. I was calling it x sub j star in my previous video, but it'd be like f of x sub I star. So like f of x is x squared, the squared function, and then this would be like x sub I. X sub I is, on the other hand, a plus I delta x. If I'm at aka equals to 2, it's easy to understand that as 2. And then my delta x would be 3 over n, which means I go from 2 to 2 plus 3. So like the upper one's going to be 5. So like 5 minus 2 over n is 3 over n. Admittedly, there's some creativity here, and this is a challenging problem. You really need to understand the definition of the definite integral to be able to think backwards a little bit. Anyway, enough about that. Integrate. These are all solvable with algebra, basic entities, and basic antiderivatives. Yeah. So, yeah. Tangent squared, secant squared minus 1. There it is. Integral of 1 over square root of 1 minus x squared, inverse sine. This is secant. Yeah, we talked about these. Omit. Omit? Why did I say omit? Huh. I don't know. I'm not sure what happened there. Oh, I remember. I made the test and then I said, I don't have quite enough room, and so like when I printed it out, I got rid of it. But I wrote the solution beforehand, so I just kept it in there. Anyway, whatever. Oh, hey, look, I did that example for you guys. It's an example I'm fond of. Integrate. Notice the absolute value. So absolute value is piecewise defined. So from 0 to pi, sign's positive. From pi to 2 pi, sign is negative. So the absolute value gives you minus. But anyway, you get 4 because each hump of sign has area bounded of 2. Suppose dg/dt gives you the rate at which cats jump out a window. What does the integral from 1 to 4 of dg/dt represent? Given that t equals 0 corresponds to noon and t is equal to t is in hours. So this is the net change theorem, which is kind of a corollary to things I've already told you guys about. But so if dg/dt is the integrand, then g is an antiderivative, right? Because g differentiates to dg/dt. So FTC part 2 says that this is equal to g of 4 minus g of 1. All right. So that's the net change in g from time 1 to time 4. Apparently, it's the total number of cats that jumped out the window from 1 p.m. to 4 p.m. So let's hope that's positive. All right. Integrate. Show work where necessary. Indicate all u substitutions either implicitly or explicitly. Here's an explicit indication of the u substitution. Here's an implicit indication of the u substitution right there. In your face. Sorry. Yep. 0 less than a less than b. Got to change the bounds, folks. Got to change the bounds, all right? If you're going to do it like this, you got to change the bounds. And, of course, the square root of a squared, the square root of b squared is just a and b because I'm given that a and b are positive. Anyway, there's that one. This one gets a lot of people. This one up here, you gotta, usually the denominator is what you want to make the u, because we do know that this, like, if you have a sum of a plus c plus d over, g, where g is in the denominator, then it's like a over g plus b over g plus c over g plus d over g. But you can't break up sums in the denominator. Like if I have a over b plus c, it is not equal to a over b plus a over c. So it pays to make u the denominator in a problem like this, and I do, and after I do that, you get u minus 1 over u, which is this, which integrates to that. All right. Don't forget to go back to x at the end. Don't forget your absolute value for sine, for natural log. Integral of cosine cubed, we've talked about that ad nauseum. You know, I could do cos or cosh cubed. It's all good. Cosine squared, 1 minus sine squared, and this, of course, is the derivative of sine x, the differential, if you will. And so there it is. I used an implicit substitution there. U was equal to sine x, if you want me to be explicit. I must have moved that in the test that's supposed to, I don't know. Anyway, it's still worth talking about. Integral of sine squared, of course, is 1/2 minus 1/2 cosine 2 theta, and you integrate theta over 2 minus 1/4 sine of 2 theta. Don't forget your plus a constant. Let's see here. Suppose that the acceleration of Herbert is given as a function of time to be a of t equal to t. Furthermore, Herbert undergoes one-dimensional motion along the x-axis where he begins at the origin with v of 0 equals 1. Calculate the velocity and position of Herbert as a function of time. So this is basically, again, a staggered pair of initial value problems. Find the velocity as a function of time by integrating acceleration, and I rewrite it as tau d tau bar. I don't know why I have the bar, but whatever. So that's 1 plus 1/2 t squared. Oh, this is, I'm being a little bit, you can derive this formula from integrating dv dt equal to t, and on the one hand you get v of t minus v of 0. On the other hand, you get the integral of 0 to t of t dt, but we shouldn't use t for both the variable integration and the fixed preparatory time. We're finding v as a function of. Anyway, however you do it, 1 plus 1/2 t squared, and then integrate again. And if you do it this way, it builds in the initial value for you. I've been showing you guys how to do it a different way. In other words, I integrate like, 1/2 t squared plus a constant, and then I put, say, v of 0 as 1, then it forces the constant to be 1. And, I integrate, I get t plus 1/6 t cubed plus a constant, and then I put x of 0 to be 0, and then that forces this to be that. So this is an equivalent way of doing it. Sometimes this way of thinking through initial value problems is better. Anyway, happy to talk to you more about it in person if you want to see more, whatever. Find the area bounded between y equals x and y equals x cubed. So include a graph in the typical infinitesimal region. Tried to show you for a few examples of these. Right. The thing about this one is that the dA on one side and the opposite side are kind of opposite, right? The line is below on the left and above on the right. But fortunately there's a symmetry here, so you can actually just calculate the area of this piece and then double it. Careful with symmetry. If it's not there and you assume it's there, you'll be wrong. Area bounded by x equals 2 minus y squared and x equals minus 2. So this is a left opening sideways parabola, and this is a vertical line. So, and that's basically the area you're trying to calculate. So I think the convenient thing to do is to do horizontal rectangles as the typical infinitesimal region. That gives me a dA of 4 minus y squared. I wonder, is that right? Wait a minute. Oh, I'm sorry. Let me go back up a step here. 2 minus y squared is the right, minus a minus 2, and that turns into 4 minus y squared. Okay, great. And then you integrate, and you get 32 over 3. A challenge theory question of sorts. Suppose a of x is the area function based at 1 for f, all right? And we're given f is continuous on the reals. Answer the questions below in view of the information just given. Feel free to use any important theorems which I presented in lecture to answer the questions above. I do mean that k is a natural number in part 3. If f is differentiable on the reals, is a also differentiable on the reals? Well, a is equal to, the derivative of a is equal to f, right? That's the fundamental theory of calculus part 1, which holds for continuous functions, at least. So yeah, A is differentiable. In fact, wait a minute. Yes. Oh. Yeah, a side consequence of that, of course, is that A is also continuous. If it's differentiable, it's also continuous, right? But the, you know, the answer stops here, and this is just extra. All right. Question 2. If f is not differentiable, then is A also a differentiable function? Let's see, if f is not differentiable, then it doesn't matter. F is given to be continuous. A is still differentiable by FTC1. FTC1 only requires f continuous. If f is not, continuous, I mean, if it's not differentiable, but it's still continuous, doesn't matter. And so, for example, if you integrate the absolute value of x, you'll end up with a function which is differentiable at 0, even though the absolute value of x is not differentiable at 0. Generally speaking, integration makes things smoother. Smooth out kinks. Question 3. If f is k times continuously differentiable, then A is k plus 1 times continuously differentiable. Again, the answer is yes, because of the fundamental theorem of calculus part 1. The k plus 1th derivative of A is the kth derivative of f because of this, and that's continuous by assumption. Consequently, a to the k plus 1th derivative of A is continuous. So basically, this question is just, do you know the fundamental theorem of calculus part 1? Let's see here. Problem 13 is kind of scary in calculus 1 terms, because like, what do I do with that? Well, you do the definition and laws of algebra. So this is e to the 2x plus 1/2, and that integrates. Done. This is 1, so x plus c. This, if you know your adding angles formula, is sine of 4 theta. Right? I'll talk more about trigonometry after these videos. Let's see here. Integral of sine cosine ax bx. There you need to know this wonderful formula that sine times a cosine is the sine of the sum of the values minus the sine of the difference of the values, all divided by 2. So there it is. Now this last one, is a challenge of pre-calculus, really, because what you have to do is to rewrite these both as 2 to the x or both as e to the x with modified arguments. I chose e. 2 to the x is e to the x ln of 2, and then you add them, and that gives you e to the ln of 2 plus 1 x dx, and there it is. I do think that stumped a fair number of students, although it's kind of at the end of the test, so most of them probably didn't get to it. Anyway, so those are, so now you have seen the suffering of Calculus 1 of 2010. That's about it. I will show you more about trigonometry in the next video. Thanks, guys.